Cosmic rebirth via black holes. The idea that black holes could be portals to new universes offers a fascinating twist to our understanding of the cosmos. This concept challenges traditional views of black holes as cosmic endpoints and instead reimagines them as gateways to beginnings. Could the Big Bang, the event that gave birth to our universe, have originated from a black hole in another universe? This question is more than a thought experiment. It touches on some of the deepest mysteries of physics and cosmology. The nature of black holes. Black holes are regions of space where gravity is so strong that nothing, not even light, can escape. At their centers lies a singularity, a point where density becomes infinite, and the laws of physics as we know them break down. Surrounding the singularity is the event horizon, the boundary beyond which nothing can return. Traditionally, black holes are seen as the ultimate cosmic traps. Matter and energy fall in, but they cannot come out. However, some theories propose that this may not be the whole story. Instead of being dead ends, black holes could be the seeds of new universes, places where space and time are reborn. The idea of cosmic rebirth. The concept of black holes as portals to new universes arises from ideas in theoretical physics, particularly in quantum gravity and cosmology. The key idea is that the extreme conditions inside a black hole could mirror the conditions of the Big Bang, a state of infinite density and energy. Some physicists suggest that when matter collapses into a singularity, it doesn't remain trapped forever. Instead, the singularity could bounce or expand, creating a new region of spacetime. From the perspective of the new universe, this expansion would look like a Big Bang. In this view, black holes are not just destructive. They are also creative, giving rise to entirely new realms of existence. Could our universe be born of a black hole? This idea raises an even more intriguing possibility, that our own universe was born from a black hole in another universe. If this is true, the Big Bang might not have been a singular event, but part of a larger cycle of cosmic creation. Each black hole could spawn a new universe, and each universe could contain black holes that give rise to others, forming a vast interconnected multiverse. One version of this theory, known as cosmological natural selection, suggests that universes with properties favorable for black hole formation might be more likely to give rise to offspring universes. This idea reframes black holes not as cosmic anomalies, but as fundamental to the process of cosmic evolution. Theoretical foundations. Several areas of physics support the idea of cosmic rebirth via black holes, though it remains highly speculative. General relativity and singularities of cosmic rebirth via black holes, though it remains highly speculative. General relativity and singularities. Einstein's equations describe the formation of singularities inside black holes. Some extensions of these equations suggest that singularities could lead to new regions of spacetime rather than being points of infinite collapse. Quantum gravity. Theories like loop quantum gravity propose that the extreme conditions near a singularity could cause a bounce rather than a collapse. This bounce might initiate the expansion of a new universe. The holographic principle. This principle, inspired by string theory, suggests that all the information about what falls into a black hole is stored on its event horizon. In a new universe, this information could form the seeds of structure and matter, entropy, and the arrow of time. Some physicists argue that the high entropy of a black hole could explain the initial conditions of a new universe. In this view, the arrow of time that governs the flow of events might reset with each cosmic rebirth. Challenges and questions. While the idea of cosmic rebirth is captivating, it faces significant challenges. For one, we currently lack direct evidence for the existence of other universes or the ability of black holes to create them. Observing what happens inside a black hole is impossible because the event horizon prevents any information from escaping. Moreover, the theory raises philosophical questions. If each black hole creates a new universe, what does that mean for the parent universe? Are we just one link in an endless chain of universes? Or is there a larger purpose or pattern to this process? These are questions that blend science with metaphysics. Implications for our understanding of the universe. The idea of cosmic rebirth via black holes shifts our perspective on the nature of reality. Instead of a universe with a single beginning and end, we might live in a multiverse where creation and destruction are interconnected. Black holes, long seen as symbols of doom, could be the engines of renewal. This theory also offers a new way to think about the Big Bang. Rather than arising from nothing, the Big Bang might be part of a larger cycle of cosmic events. It suggests that our universe is not isolated, but part of a vast, interconnected web of space-time, a window into the unknown. The idea that black holes could lead to new universes is speculative, but it is grounded in serious physics. It pushes the boundaries of what we know and challenges us to think beyond traditional ideas about space, time, and existence. While we may never fully understand the nature of black holes or the origins of the universe, exploring these questions brings us closer to understanding our place in the cosmos. The theory of cosmic rebirth is not just about black holes or the Big Bang. It is about the nature of creation itself. It suggests that even in the darkest corners of the universe, there may be the potential for new beginnings. And perhaps in the end, this is the most profound lesson of all, that endings are never truly the end, but the start of something new. Reversible versus irreversible black hole growth. Black holes are among the most enigmatic objects in the universe. They grow by absorbing matter and energy, becoming larger and more massive as they consume their surroundings. This growth seems straightforward. Once matter crosses the event horizon, the boundary of a black hole, it can never escape. But is this process entirely irreversible? Or could there be circumstances where a black hole's growth is, in some sense, reversed? This question probes the nature of black holes and the dynamics that govern them, blending ideas from thermodynamics, quantum mechanics, and general relativity. How black holes grow. When a black hole absorbs matter or energy, its mass increases, and so does the size of its event horizon. The event horizon is directly proportional to the black hole's mass, making this growth a measurable and predictable process. This growth occurs in several ways. Accretion of matter, gas, stars, or any other form of matter spiraling into the black hole adds to its mass. Merging with other black holes. When two black holes collide, they combine their masses, forming a larger black hole. Absorption of energy, even radiation, like photons, can contribute to a black hole's growth. These processes are governed by Einstein's theory of general relativity, which describes how the curvature of space-time around the black hole changes as it grows. Once matter passes the event horizon, it is forever cut off from the outside universe, seemingly making black hole growth an irreversible process. The question of reversibility. On the surface, black hole growth appears irreversible. The event horizon acts as a one-way gate. Anything that enters cannot come back out. However, deeper exploration reveals that the question is more nuanced. Reversibility in this context does not necessarily mean shrinking the black hole or undoing its growth in a literal sense. Instead, it involves examining whether certain dynamics might allow for information or energy to escape, effectively reversing the consequences of growth. Thermodynamic perspective. Black holes obey the laws of thermodynamics, with their surface area corresponding to entropy, a measure of disorder. The second law of thermodynamics states that entropy always increases in an isolated system, suggesting that black hole growth is fundamentally one way. However, processes like Hawking radiation, where black holes emit energy and gradually lose mass, challenge this notion. Hawking radiation has reversal. Over incredibly long timescales, black holes can evaporate due to Hawking radiation. This process gradually reduces their mass, shrinking the event horizon. While this does not restore the original matter that fell in, it is a kind of reversal in the sense that the black hole's growth is undone. Quantum considerations. Quantum mechanics introduces the possibility that information about matter and energy absorbed by a black hole might not be lost forever. Some theories propose mechanisms by which information encoded in a black hole could be released back into the universe, partially reversing the effects of growth. Black hole information paradox. If information about absorbed matter escapes through Hawking radiation, it would mean that some aspect of the black hole's growth, its increase in entropy, is not irreversible. Reversibility in dynamic systems. The environment around a black hole can also influence whether growth is strictly one way. For example, superradiance, a process where black holes lose energy by interacting with certain types of waves or fields. In these cases, energy is extracted from the black hole, causing a small but measurable decrease in its rotational energy or mass. Tidal disruption events. While these typically result in a black hole gaining mass, the dynamics of such events can redistribute energy and angular momentum in ways that complicate the idea of simple, irreversible growth. Hypothetical scenarios. Some theoretical models suggest that under certain conditions, black holes might interact with their surroundings in ways that mimic reversibility. For example, wormholes in exotic physics. If black holes are connected to other regions of spacetime, as in wormhole models, it might be possible for matter or information to exit, effectively reversing some aspects of growth. Black hole bounce certain speculative theories, like loop quantum gravity, propose that black holes might transition into different states or even bounce, returning some of their matter or energy to the universe. Irreversibility in practice. Despite these theoretical possibilities, the overwhelming evidence suggests that black hole growth is practically irreversible. Matter that crosses the event horizon is permanently removed from the observable universe, and any processes that could reverse this are either extraordinarily slow, like Hawking radiation, or purely hypothetical. In everyday terms, the black hole's growth is a one-way street. Deeper implications. The question of reversibility goes beyond black holes themselves. It touches on fundamental ideas about the nature of time, entropy, and causality. Entropy and the arrow of time. Black hole growth mirrors the thermodynamic arrow of time, emphasizing the unidirectional nature of many physical processes. Unification of physics, resolving the tension between quantum mechanics and general relativity in the context of black hole dynamics, could lead to a deeper understanding of the universe. Black holes grow by absorbing matter and energy, and this process appears irreversible from most perspectives. However, quantum mechanics and advanced theoretical models suggest that some aspects of this growth might be reversed under specific conditions. Whether through Hawking radiation, quantum information recovery, or exotic physics, the notion of reversibility challenges our understanding of black holes and the universe's fundamental laws. Gravitational wave information lost. The merging of two black holes is one of the most extreme and energetic events in the universe. During this process, massive amounts of energy are released as gravitational waves, ripples in the fabric of spacetime. These waves, first detected in 2015 by the LIGO Observatory, have revolutionized our understanding of the cosmos. But they also raise a fundamental question. Do gravitational waves carry away the information about the black holes that produce them? Or is that information lost forever? This question sits at the intersection of quantum mechanics, general relativity, and information theory. The problem: gravitational waves are produced when massive objects, like black holes, interact in violent ways. In the case of black hole mergers, these waves carry energy and momentum away from the system, eventually leading to the formation of a single larger black hole. The emitted waves encode certain details about the event, such as the masses, spins, and orbital dynamics of the merging black holes. However, they do not seem to carry all the information about the internal states of the original black holes. This apparent loss of information creates a potential paradox. Quantum mechanics insists that information cannot be destroyed even in the most extreme conditions. But general relativity, the theory that governs black hole behavior, does not explicitly preserve this rule. If information about the black holes is lost during the merger, it challenges our understanding of how the universe preserves and processes information. Why it matters? The question of information loss in gravitational waves is not just a technical curiosity. It has profound implications for our understanding of the universe. At stake is the principle of information conservation, a cornerstone of quantum mechanics. If gravitational wave events lead to a loss of information, it would suggest that quantum mechanics is incomplete or that our understanding of black holes and gravitational waves needs significant revision. Additionally, this issue ties into the broader black hole information paradox, which asks what happens to information when objects fall into a black hole. If gravitational wave emissions fail to preserve all the information from merging black holes, it might indicate that black holes are more mysterious than we currently realize. What information do gravitational waves carry? Gravitational waves are highly informative, but only about certain aspects of the system. When LIGO and other detectors observe these waves, they can extract details such as masses and spins. The gravitational waves reveal the masses of the merging black holes and how fast they were spinning. Orbital dynamics, the shape of the waves, tells us about the orbits of the black holes before the merger. Final black hole properties, the resulting black hole's mass, spin, and energy loss can also be inferred. These observations are remarkably precise, but they do not capture every piece of information about the merging black holes. For instance, the internal quantum states of the black holes, or detailed information about their formation histories, do not appear to be encoded in the waves. This leaves open the possibility that some information is lost during the merger. Possible resolutions. Physicists have proposed several ideas to address the question of information loss in gravitational waves. Gravitational waves as partial carriers of information. It is possible that gravitational waves only carry a subset of the information about the merging black holes. The rest of the information might remain encoded in the black hole that forms after the merger. This idea aligns with the notion that black holes themselves store information in their event horizons, as suggested by the holographic principle. Quantum corrections to gravitational waves. Some theories suggest that gravitational waves might carry more information than we currently detect. Quantum effects near the black hole horizons could subtly influence the waves, encoding additional details. Advanced detectors and new theoretical insights might uncover these hidden signatures in the future. Information encoded in the final black hole. Another idea is that all the information from the merging black holes is retained in the final black hole, but in a form we do not yet fully understand. If the final black hole's properties include quantum imprints from the original black holes, information might not be lost. It could just be inaccessible with current methods. Limits of current observations. It is also possible that gravitational waves carry all the information, but our current detectors are not sensitive enough to extract it. Future gravitational wave observatories, such as the space-based LISA mission, might detect subtle features that resolve this issue. New physics. The apparent loss of information in gravitational waves might point to new laws of physics. These laws could unify quantum mechanics and general relativity, providing a deeper understanding of black hole mergers and gravitational wave emissions. Broader implications. This question touches on some of the biggest mysteries in physics. Resolving whether gravitational waves preserve all information could help bridge the gap between general relativity and quantum mechanics, two theories that currently operate in separate realms. It could also shed light on the nature of black holes, including whether they truly destroy information or simply encode it in ways we do not yet understand. Beyond physics, this issue has philosophical implications. Information is central to how we understand the universe. If information can be lost, even in extreme cases like black hole mergers, it challenges our ability to reconstruct the past and predict the future. What the paradox teaches us. The question of gravitational wave information loss reminds us that the universe still holds deep mysteries. It forces us to question our assumptions about how nature works, even in areas where our theories seem well established. At the same time, it highlights the incredible progress we've made. Just a few decades ago, gravitational waves were purely theoretical, and today we use them to study the cosmos. Ultimately, this issue is not just about black holes or gravitational waves. It is about the limits of knowledge and the nature of reality itself. By exploring these questions, we are not only seeking answers to specific problems, but also pushing the boundaries of what we know about the universe. The black hole to white hole transition. The idea of a black hole transitioning into a white hole is a fascinating hypothesis that challenges conventional thinking about how black holes behave as they evaporate. While black holes are known for pulling everything in with their immense gravity, white holes are theoretical objects that do the opposite, repelling matter and light, making them impassable in reverse. Some scientists propose that, under certain conditions, a black hole might transform into a white hole during the final stages of its life. This hypothesis raises intriguing questions about the nature of black holes, the flow of time, and the fundamental laws of physics. The core hypothesis. The concept of a black hole turning into a white hole arises from attempts to address two key problems in physics. The fate of black holes. According to Stephen Hawking's groundbreaking work, black holes slowly lose mass through Hawking radiation, a quantum process where energy escapes in the form of particles. Over time, this process causes the black hole to shrink and eventually to evaporate completely. But what happens to the matter and information trapped inside the black hole? If the black hole vanishes entirely, it appears that all this information is lost, leading to the information paradox. Time symmetry in physics. Many of the fundamental laws of physics, particularly those in quantum mechanics, are time reversible. This means they work the same whether time moves forward or backward. A white hole, which is essentially the time-reversed counterpart of a black hole, could offer a way to preserve information while respecting these laws. Some researchers suggest that during the final moments of its evaporation, a black hole could bounce instead of completely disappearing. This bounce would cause it to transition into a white hole, potentially expelling the trapped matter and information in a burst of energy. This process could resolve the information paradox by allowing the information to escape rather than being destroyed. Theoretical foundations. The idea of a black hole to white hole transition is grounded in speculative but intriguing physics. Here are some of the key ideas that support this hypothesis. Loop quantum gravity. Loop quantum gravity is a theoretical framework that seeks to merge quantum mechanics with general relativity. In this theory, spacetime itself has a discrete, granular structure. This granularity could prevent the formation of a singularity, the point of infinite density predicted at the center of a black hole. Instead, as the black hole evaporates, the extreme conditions near the singularity might cause a quantum bounce, reversing the collapse and triggering a transition into a white hole. Spacetime geometry. The equations of general relativity allow for the existence of white holes as solutions, just as they allow for black holes. While no white holes have been observed, the symmetry of the equations suggests they are at least theoretically possible. A black hole transitioning into a white hole would respect this symmetry, while also addressing the question of where the information goes. Entropy and information recovery. A black hole has entropy, which is a measure of the information it contains. If a black hole becomes a white hole, the information trapped inside could be released as the white hole ejects its contents. This process would preserve the total information in the universe, aligning with the principles of quantum mechanics. Evaporation timescale. Black holes take an extraordinarily long time to evaporate completely. For a stellar mass black hole, this process could take far longer than the current age of the universe. However, as the black hole shrinks to microscopic sizes during the final stages of evaporation, quantum effects might dominate, making a transition to a white hole more plausible. Challenges and open questions. While the idea of a black hole transitioning into a white hole is intriguing, it faces several significant challenges. Lack of evidence. White holes remain entirely theoretical. No astronomical observations have ever identified an object behaving like a white hole, and there is no direct evidence that black holes undergo such a transition. Stability of white holes. Theoretical models suggest that white holes would be extremely unstable, quickly collapsing under their own gravity or the influence of nearby matter. This instability raises questions about whether a black hole to white hole transition could produce a long-lived white hole. Energy and dynamics. The energy released during such a transition would be enormous, possibly resulting in a powerful burst of gamma rays or other radiation. However, predicting the exact dynamics of this process requires a complete theory of quantum gravity, which we do not yet have. Role of Hawking radiation. The transition hypothesis must account for Hawking radiation, which steadily reduces a black hole's mass. How this gradual evaporation interacts with a sudden transition to a white hole is not fully understood. What it could mean. If black holes can transition into white holes, it would have profound implications for physics and our understanding of the universe. Resolution of the information paradox. A black hole to white hole transition could provide a mechanism for preserving and releasing information, addressing one of the biggest unresolved questions in physics. Insights into quantum gravity. Such a process would offer valuable clues about the nature of spacetime at the smallest scales and could help unify quantum mechanics and general relativity. Cosmological connections. Some theories suggest that white holes could play a role in the early universe, potentially explaining certain features of cosmic evolution. Conclusion. The hypothesis that black holes might transition into white holes during their final stages is a bold and exciting idea. While it remains speculative, it challenges us to think beyond our current understanding of black holes and the nature of spacetime. It forces physicists to grapple with the limits of our theories and to explore the connections between gravity, quantum mechanics, and the flow of time. Quantum gravity and black holes. Quantum gravity is the quest to unify two of the most important theories in physics, quantum mechanics and general relativity. These theories describe the universe on vastly different scales. Quantum mechanics governs the behavior of the tiniest particles, while general relativity explains the motion of stars, planets, and galaxies. When it comes to black holes, these two frameworks clash. A unified theory of quantum gravity might resolve their contradictions and answer some of the biggest questions in physics. The conflict between two theories. General relativity describes black holes as regions of space where gravity is so intense that nothing, Not even light can escape. At the center of a black hole lies a singularity, a point where gravity becomes infinite and space and time cease to exist in their usual forms. Around the singularity is the event horizon, a boundary that marks the point of no return. General relativity predicts the structure and behavior of black holes with remarkable precision, but it breaks down at the singularity. Quantum mechanics, on the other hand, governs the behavior of down at the singularity. Quantum mechanics, on the other hand, governs the behavior of particles at the smallest scales. It introduces the idea that particles exist in a state of probability and that information about a system is always preserved. However, when we try to apply quantum mechanics to the extreme environment of a black hole, it leads to contradictions. For example, quantum mechanics insists that information cannot be destroyed, but black holes appear to erase all information about what falls into them. This is the root of the information paradox. Why quantum gravity is needed. The conflict between quantum mechanics and general relativity becomes unavoidable in extreme conditions, such as the center of a black hole or the early moments of the universe during the Big Bang. These are situations where the immense gravity described by general relativity interacts with the tiny scales of quantum mechanics. Neither theory alone can fully describe these conditions. A theory of quantum gravity aims to bridge this gap. Quantum gravity would combine the strengths of both theories. It would explain how gravity operates at quantum scales and provide a unified framework to describe phenomena like black holes. If successful, it could resolve long-standing puzzles, such as what happens to the information that falls into a black hole and what lies beyond the singularity. Challenges in developing quantum gravity. Creating a theory of quantum gravity is one of the hardest problems in physics. Both general relativity and quantum mechanics are well tested and highly accurate in their respective domains, but they use fundamentally different mathematical frameworks. General relativity treats space and time as a smooth, continuous fabric, while quantum mechanics works with discrete particles and probabilities. Reconciling these approaches requires a new way of thinking about space, time, and gravity. Proposed theories of quantum gravity. Physicists have proposed several ideas to develop a theory of quantum gravity, each offering unique insights into the nature of black holes. String theory. String theory suggests that the fundamental building blocks of the universe are not particles, but tiny vibrating strings. These strings exist in multiple dimensions beyond the three we experience. String theory can describe gravity at quantum scales and has led to concepts like the holographic principle, which suggests that all the information about a black hole is stored on its two-dimensional surface, the event horizon. Loop quantum gravity. This approach focuses on quantizing space and time directly. It proposes that space is made up of tiny discrete units, like pixels in a digital image. In loop quantum gravity, the singularity at the center of a black hole may not exist. Instead, there might be a quantum structure that avoids the infinite density predicted by general relativity. Black hole complementarity be a quantum structure that avoids the infinite density predicted by general relativity. Black hole complementarity. This idea suggests that the information falling into a black hole is both preserved on the event horizon and passes through to the interior, depending on the observer's perspective. This dual description could reconcile the contradictory predictions of general relativity and quantum mechanics. Emergent gravity. Some researchers believe that gravity might not be a fundamental force, but an emergent property arising from quantum interactions. In this view, black holes could be explained as collective phenomena rather than singular objects. Implications for black holes. A theory of quantum gravity would radically change our understanding of black holes. It could explain what happens at the singularity and whether it even exists. It might also show how information escapes from a black hole, resolving the information paradox. Additionally, quantum gravity could reveal whether black holes are connected to other regions of the universe, or even other universes. If quantum gravity can describe the interior of a black hole, it may also explain what happens during the final stages of Hawking radiation. Does the black hole evaporate completely, leaving no trace, or does it leave behind a remnant that contains the information it consumed? These are questions that only a unified theory can answer. Broader implications. The search for quantum gravity extends beyond black holes. It could provide insights into the origins of the universe, the nature of time, and the fundamental structure of reality. By reconciling the smallest and largest scales of the universe, quantum gravity could reveal new laws of physics that apply everywhere, from subatomic particles to the cosmos itself. A frontier in physics. The study of quantum gravity in black holes is not just about solving mathematical equations. It is about understanding the universe at its most fundamental level. It challenges us to rethink space, time, and the forces that shape the cosmos. While physicists have made progress, the complete theory remains elusive. The journey to quantum gravity is as much about asking new questions as it is about finding answers. Black holes, once thought to be simple objects defined by their mass, spin, and charge, are now seen as laboratories for testing the limits of our knowledge. They are places where the mysteries of gravity and quantum mechanics collide, offering a glimpse of the deeper truths that lie beyond our current understanding. Solving these mysteries could transform physics and give us a clearer picture of the universe and our place within it. Cosmic censorship conjecture. The cosmic censorship conjecture is a big idea in physics that helps us understand how the universe stays predictable and orderly. It suggests that the most extreme points in the universe, called singularities, are always hidden behind the boundaries of black holes. These boundaries are known as event horizons. Singularities are places where gravity becomes infinitely strong and the normal rules of physics break down. The conjecture works like a safety shield. It prevents us from seeing or being affected by the chaotic, unpredictable nature of singularities. If this conjecture is correct, the universe is protecting us from its most bizarre and unpredictable secrets. But what if this shield fails? What if a black hole reveals its singularity, creating what is called a naked singularity? This question challenges our understanding of how the universe works and has led to years of research and debate among scientists. What is a singularity? To understand the cosmic censorship conjecture, we need to know what a singularity is. In Einstein's theory of general relativity, a singularity is a point where gravity becomes so strong that it causes space-time, the fabric of the universe, to curve infinitely. At this point, the known laws of physics stop working, and we can't predict what might happen. Singularities are thought to exist at the center of black holes. However, black holes have an event horizon, a boundary that traps everything inside, including light. This event horizon keeps the singularity hidden, so its effects don't escape to the rest of the universe. A naked singularity is a singularity without, so its effects don't escape to the rest of the universe. A naked singularity is a singularity without an event horizon. It's exposed to the universe, and if it exists, it could create chaos and disrupt the normal rules of physics. Why is the cosmic censorship conjecture important? The cosmic censorship conjecture was proposed by physicist Roger Penrose in 1969. It suggests that nature always hides singularities behind event horizons, keeping them out of sight and preventing them from directly affecting the rest of the universe. This conjecture is important because it preserves the predictability of the universe. If singularities could be observed or interact with the universe, the normal flow of cause and effect could break down. This would make it impossible to predict events in the universe, which is a key part of how science works. The conjecture has two main forms. Weak cosmic censorship. Singularities created by collapsing stars or matter are always hidden behind event horizons. Strong cosmic censorship. Even in extreme situations, singularities remain hidden and space-time remains predictable. If the conjecture is true, it ensures that the universe remains orderly and that the breakdown of physics at singularities doesn't affect the rest of the cosmos. What happens if a naked singularity appears? If a naked singularity exists, it could have serious consequences for our understanding of the universe. Here's what might happen. Loss of predictability. Science relies on the idea that we can predict the future of the universe based on its current state. A naked singularity would create regions where the laws of physics no longer work, making the future unpredictable. Exposure to infinite energies. At a singularity, physical quantities like density and gravity become infinite. If a singularity were exposed, these infinite values could interact with the universe in ways we can't imagine, potentially causing chaos. Violations of cause and effect. A naked singularity could create time loops or other situations where the normal flow of cause and effect breaks down. For example, an event might happen before its cause, leading to paradoxes. Opportunities for new discoveries. While naked singularities might seem scary, they could also help us learn more about the universe. Observing a naked singularity could give scientists a chance to study physics in extreme conditions and develop new theories, like quantum gravity, that combine general relativity and quantum mechanics. Do naked singularities exist? Whether naked singularities exist is still an open question. The cosmic censorship conjecture is widely accepted, but it hasn't been proven. Scientists have explored several scenarios where naked singularities might form. Rotating black holes. A rapidly spinning black hole called an extremal Kerr black hole might lose its event horizon and expose its singularity. However, it's unclear if such black holes can exist in nature. Exotic collapses. In certain extreme situations, like highly energetic or unbalanced collapses of matter, singularities might form without event horizons. These conditions are rare and may not happen in the observable universe. Computer simulations suggest that naked singularities could form in specific, carefully controlled situations. However, these simulations often rely on idealized assumptions that may not reflect reality. Why this matters for physics: the cosmic censorship conjecture represents more than just a safeguard. It reflects a belief that the universe is fundamentally orderly. If the conjecture is correct, it means the universe has mechanisms to hide its most chaotic features, keeping its laws consistent and predictable. But if naked singularities exist, they could reveal new aspects of the universe. They might force us to rethink our current understanding of gravity, space-time, and quantum mechanics. In particular, they could help us develop a unified theory of quantum gravity, which combines general relativity and quantum mechanics. The debate over the cosmic censorship conjecture also highlights the limits of our current knowledge. Neither general relativity nor quantum mechanics can fully explain what happens at a singularity. Solving this mystery could lead to groundbreaking discoveries about the universe's most extreme and mysterious places. What the conjecture teaches us. The cosmic censorship conjecture reminds us that there's still much we don't know about the universe. It challenges scientists to push the boundaries of our understanding and explore new ideas about space, time, and gravity. Whether or not the conjecture is true, it forces us to confront the big questions. How does the universe handle its most extreme conditions? Are the laws of physics complete, or do we need new ones? What would happen if the universe revealed its most chaotic secrets? These questions show that physics isn't just about solving equations. It's about understanding the deepest mysteries of the cosmos. Black hole remnants. The idea of black hole remnants is a fascinating concept in science. It could help solve one of the biggest mysteries in physics. What happens to information when a black hole disappears? Black holes are regions in space where gravity is so strong that nothing, not even light, can escape. Over time, they slowly shrink and evaporate by giving off energy, called Hawking radiation. But what happens when a black hole vanishes completely? Some scientists believe it doesn't disappear entirely, but leaves behind a tiny stable object called a black hole remnant. These remnants might hold the key to solving the information paradox. What is the information paradox? The information paradox is a big problem in physics. It comes from a disagreement between two major theories. Quantum mechanics says that information about a physical system can never be destroyed. Even if something changes form, the information about it must always exist somewhere. General relativity says that black holes eventually evaporate completely, leaving no trace of what fell into them. This creates a contradiction. If black holes disappear, what happens to the information they swallowed? Does it vanish too? According to quantum mechanics, this can't happen. But general relativity seems to suggest it does. This is the information paradox. How could black hole remnants help? The idea of black hole remnants offers a simple solution. When a black hole shrinks and loses almost all of its mass, it doesn't completely disappear. Instead, it becomes a tiny stable remnant. This remnant could act like a storage device, holding all the information about what fell into the black hole during its lifetime. If this is true, it solves the information paradox because the information isn't lost. It's just stored in the remnant. This idea fits with the rules of quantum mechanics, while also respecting the predictions of general relativity. What are black hole remnants? Black hole remnants are hypothetical, not yet proven, objects that would remain after a black hole has evaporated. Scientists think they would be extremely small and dense, possibly as small as the Planck scale, the smallest size in the universe, where quantum effects are strongest. Stable. Unlike black holes, remnants wouldn't shrink or change. They'd last forever, preserving the information they contain. While we don't know much about how these remnants would work, they could store all the information from the black hole's entire existence. If this is true, they would solve the paradox by giving information a place to exist even after the black hole itself is gone. Challenges and questions about remnants. The idea of black hole remnants is exciting, but it also raises many tough questions. How is the information stored? Black holes can grow very large and swallow massive amounts of matter and energy. If a remnant is incredibly tiny, how can it store all this information? Our current understanding of physics doesn't explain how this might work. Information. Our current understanding of physics doesn't explain how this might work. Are remnants stable? For remnants to solve the paradox, they must last forever. But we don't know if such tiny objects can remain stable. Physics at the smallest scales, the Planck scale, is still a mystery. Can we detect remnants? Remnants would be very small and dense, making them almost impossible to observe with current technology. However, their existence might have subtle effects like influencing the behavior of Hawking radiation or creating tiny changes in spacetime. Do remnants follow the rules of physics? If remnants store vast amounts of information, does this fit with the laws of energy conservation and other principles of physics? Scientists are still debating these questions. Why do black hole remnants matter? If black hole remnants are real, they would do more than solve the information paradox. They could give us new insights into some of the deepest mysteries in science. Unifying quantum mechanics and general relativity, remnants could help bridge the gap between these two major theories, showing how they can work together. Understanding space and time. Studying remnants might reveal new laws of physics that explain how space, time, and matter behave at the smallest scales. Exploring the fate of black holes, remnants could show us what happens to black holes in the very end, answering questions that have fascinated scientists and the public for decades. Are black hole remnants the answer? While remnants are an interesting idea, they are just one of several possible solutions to the information paradox. Other theories include the holographic principle suggests that all the information about a black hole is stored on its surface, not inside it. Hawking radiation carries information proposes that Hawking radiation isn't random and might slowly release information back into the universe. New physics beyond our understanding. Some scientists think the paradox shows we need to discover new laws of physics. Each idea has its strengths and weaknesses, and none have been proven yet. But remnants are appealing because they offer a simple explanation. Black holes leave behind a physical object that holds all the information they absorbed. What's next? The study of black hole remnants is still theoretical, but it pushes the boundaries of what we know about the universe. If remnants exist, they could reshape our understanding of physics and answer some of the most profound questions about space, time, and reality. For now, they remain a mystery, but one that scientists are eager to solve. A mystery, but one that scientists are eager to solve. EREPR conjecture paradox. The EREPR conjecture is a fascinating idea in modern physics that links two puzzling phenomena, wormholes and quantum entanglement. It was introduced in 2013 by physicists Juan Meldacena and Leonard Susskind, who proposed that these two seemingly unrelated concepts might actually be the same thing. Here's the basic idea. Every pair of entangled particles is connected by a tiny wormhole, also known as an Einstein-Rosen bridge. This connection isn't something you could use to travel or communicate, but it offers a deep link between how quantum particles behave and the structure of spacetime itself. Breaking down EREPR. To understand the EREPR conjecture, let's unpack the terms. Einstein-Rosen bridges. These are wormholes, hypothetical shortcuts through spacetime that could connect two distant points. Albert Einstein and Nathan Rosen first proposed them in 1935 as a solution in general relativity. Entanglement, where two particles become linked in such a way that the state of one particle instantly affects the state of the other, no matter how far apart they are. The conjecture says these two ideas are deeply related. Entangled particles are connected by microscopic wormholes. These wormholes aren't big enough to travel through, but represent a geometric connection in spacetime. Where did this idea come from? The EREPR conjecture builds on earlier discoveries, Einstein-Rosen bridges, wormholes. Einstein and Rosen introduced wormholes as a mathematical solution in general relativity. These bridges theoretically connect two regions of spacetime, but were initially thought of as purely hypothetical. The EPR paradox. Quantum entanglement. Around the same time, Einstein, Boris Podolsky, and Nathan Rosen described quantum entanglement. They called it spooky action at a distance because it suggested particles could instantly affect each other, even if separated by vast distances. In 2013, Meldesena and Susskind proposed that these two ideas are connected. The entanglement between particles is the same as a wormhole linking them. This unites two of Einstein's ideas in a surprising way. Why is ER equals EPR important? The ER-EPR conjecture is a big deal because it connects two of the most successful but separate theories in physics. General relativity describes gravity and the behavior of large objects like stars and black holes. Quantum mechanics explains the behavior of tiny particles like atoms and photons. These two theories are incredibly accurate in their own areas, but they don't work well together. The ER equals EPR conjecture suggests a deeper connection between them, offering a step toward a unified theory of physics, sometimes called quantum gravity. What does this mean for black holes? The ER-EPR conjecture has specific implications for black holes, where quantum mechanics and relativity collide most dramatically. Entangled black holes. According to the conjecture, two entangled black holes might be connected by a wormhole. This wormhole wouldn't be traversable. You couldn't travel through it, but it would represent a hidden link in space-time. Hawking radiation and the information paradox. Black holes emit radiation, called Hawking radiation, and slowly evaporate over time. The ER-EPR conjecture could help explain how information about what fell into the black hole escapes, addressing the long-standing information paradox. If particles emitted as Hawking radiation are entangled with the black hole, their wormhole connection might preserve the information. By linking quantum entanglement to the geometry of spacetime, the conjecture offers a new way to understand the mysteries of black holes. Challenges and open questions. While the ER equals EPR conjecture is an exciting idea, it's still just a hypothesis, and many questions remain. Can it be tested? Wormholes, if they exist, are incredibly tiny and would be impossible to observe with current technology. This makes the conjecture hard to prove experimentally. What are the limits? The conjecture works well in simplified models like theoretical black holes, but scientists don't yet know how it applies to more complex systems or real-world conditions. How does it fit into quantum gravity? The ER equals EPR conjecture is a piece of the larger puzzle of quantum gravity. Scientists are still figuring out how it connects to other ideas, like string theory or loop quantum gravity. What can we learn from ER equals EPR? The ER-EPR conjecture isn't just a technical idea, it's a new way of thinking about the universe. It suggests that the geometry of spacetime, wormholes, and the strange behavior of quantum particles, entanglement, are deeply connected. This idea challenges the traditional boundaries between relativity, big things, and quantum mechanics, small things. It encourages scientists to think creatively and explore unexpected links between different areas of physics. The conjecture also highlights how progress in science often comes from combining ideas that seem unrelated. By linking wormholes and entanglement, Meldesena and Susskind have opened new doors for understanding the deepest mysteries of the universe. In the end, EREPR teaches us that the universe is full of surprising connections, and that the answers to big questions often lie in places we never thought to look.